Okay, so the presentations for this week are up, and so you should be at least part of the way through watching those. And so you would have noticed that we have switched your focus now. We've looked at Babylon and ancient Egypt, and now we're looking at classical Greece. And so there's a few things that we need to notice. It's kind of important. I started talking on Tuesday this whole idea about constructible geometry, constructible mathematics, and this is where you can solve problems by using a straight edge and compass, including algebra problems. And we'll get more later on about how you actually define algebra problems as geometry problems. That's explained quite well in Euclid. But there's a couple of things to mention about that. The first thing is that to the ancient Greek, to classical Greece, constructible mathematics kind of was mathematics. It was this kind of geometry. And they quickly got frustrated because it turned out that there are certain problems that you couldn't solve using constructible mathematics. So someone talked about that. I don't know who did the three. You did the three classical, right? So there were things like getting an arbitrary angle. How do you trisect it? How do you duplicate a cube? And duplicate here means doubling the cube. So getting a cube and making another cube of twice the volume, right? So if you just double the sides, of course, you'll get a cube that's 8 times bigger. And to get a cube that's twice the volume, you need to have a side which is the sort of the cube root of 2 times the side of the initial cube. And then there was another problem, which was the quadrature of the circle. So we've already seen that they could do the quadrature of the rectangle, so they could turn a rectangle into a square just by taking a square root. So these actually turned out to be impossible to do, and it wasn't until the 19th century that it was actually proven that those kinds of problems were insolvable. But of course it gave, we'll see that hard problems, problems that are difficult to solve, even impossible problems, give a lot of stimulus to sort of developing new ideas. And so, for example, one of the things that they developed were the conic sections. So, I don't know, people how familiar with Anna, have you seen conic sections, like the parabola and the ellipse and the, I don't know if you might not have seen it, but anyway, it's these are kind of a further level of curves rather than just the straight line and circles. It was kind of like the next collection of things that they added to their repertoire. And the impetus for this was solving those problems that they couldn't solve. So even though they end up couldn't solving them, they actually introduced a whole lot of new mathematics, which is very rich and interesting. The other thing that I wanted to emphasize was this whole idea of incommensurables. I don't know if I don't think I've spelled it right there anyway. Which is kind of their concept of irrationality. So since they were interested in geometry, they were interested, the geometry sort of is very tied in with kind of measuring things. You want to know the length of things, you want to know the area, you want to know the volume. And so this whole idea of what does measurement mean? Well, measurement means that you've got some kind of ruler and you've got marked on that ruler, you've got inches or centimeters or whatever. You've got something that you can measure things with. And so we've got this idea of a common measure that two things are commeasurable means, well, I've got it here. They have a common measure means you've got two quantities. Well, one of the basic things we want to have for a quantity is the fact that you can double it or triple it, that you can multiply it really by any positive integer just by getting more of the things. So if we're given two quantities A and B, and let's just assume that A is bigger than B, and so A and B, don't think of them as numbers, they're any kind of quantity. So they could be lengths, they could be volumes, areas, etc. And we want to find their common measure. And by that common measure, we mean some quantity x, such that it exists integers m and n, such that a equals mx and b equals nx. So x measures both of them. Okay, and the way they solved this, they actually had a method called, which we call the Euclidean algorithm. It definitely wasn't invented by Euclid. We just call it Euclidean algorithm because he was the one who wrote about it. But this was a really core concept for them. So you start off with two quantities. One is bigger than the other. So that means you can remove the smaller one from the bigger one. And that gives you a new pair of things to compare. Now, if the two things are now equal, you stop, because B is now the common measure of those two things. So the thing is, if you want the common measure of A and B, it's going to be the same thing as the common measure of A minus B and B, right? Because, because if X is the common measure of A and B, then X is also going to be the common measure of this, right? Because A minus B is going to equal M minus N times X. So X is going to measure A minus B if it measures A and B. Okay, now, if these two things aren't equal, then you just repeat the process. You replace A and B by this pair, although you've got to be careful, you've got to think which is the bigger one. So if A minus B is bigger than B, it's the new A1, but if B is bigger than A minus B, then B is the new A1. And you just repeat this process over and over again. Okay? Now, so whenever you have an algorithm, you've got to worry about when is it going to stop. And it is going to stop if there does exist a common measure. You've got to find it a finite number of times, because if you think about it, so if A divided by B lies between two integers, let's say n and n plus 1, then after n steps, B is going to turn out to be the biggest thing there. It's going to be the new A. And the new B is going to be quite a bit smaller than the old. It's going to be less than half. Hang on. Let me get this straight. All right, and so eventually you're going to get a new A, and that new A is going to be less than half of the old A. So that means that the thing has to shrink down, and since they're both positive quantities, you sort of can't go forever if there is that common measure. I didn't explain that very well, but that's true. However, there is a possibility that it doesn't stop. And it doesn't stop if there is no common measure, in which case we say things are incommensurable. And for us, this is equivalent to the idea of irrationality, that A divided by B as numbers, well, if they were numbers, that would be an irrational number. Okay, so let's look at an example of some things that you can't, that doesn't have a common measure. So let's have a look at the golden ratio. So last time we showed that the golden ratio was incommensurable by looking at a pentagon. And looking inside the pentagon, there was a golden triangle, and we went from that golden triangle and we then constructed a smaller golden triangle. And that showed that we could go on forever. A more kind of direct way is if we look at the golden rectangle, which is the rectangle whose large side to small side is the golden ratio. And so the definition of the golden ratio is that this large rectangle here is similar to this small rectangle there. And the way that you get the small rectangle is you cut out this square here. But cutting out a square is the same thing as subtracting A from A plus B. So it's the same thing as doing the Euclidean algorithm. And so if we look at this and try to do the Euclidean algorithm then between this side and this side, we then take off a square here. That would be subtracting the smallest thing. We're left still with a similar rectangle. So that means we can cut out another square and we're left with a similar rectangle. And so we can just go on forever. And this process kind of never stops. And using this process, you can actually calculate what the golden ratio is, right? So that would mean that x, if we let A be 1, and hang on, what am I going to do? So if I let A be 1, B be x, then we have 1 plus x over 1 equals 1 over x. And so then when we cross multiply, you see we have a quadratic equation which we can solve then for x equals square root. So x equals minus a half plus square root of 5 on 2. So that's that b there. So that means the whole phi, then the golden ratio, is then we add 1 to that. It's 1 plus square root of 5 on 2, which is around 1.618. Has everyone done this kind of thing before, seen the golden ratio? It's something that people do. Okay. So we can also prove that the square root of 2 is irrational by the same kind of thing. I'm very proud of this. It took me like half an hour on paint to make this picture. So here we've got a rectangle, and this is square root of 2 to 1. So this is the side of the square, and this is the diagonal of the square. So we've made a rectangle out of the side of the square and the diagonal of the square. And so then we do the Euclidean algorithm, right? So the first thing we do is we remove one side of the square from the diagonal, and that's the same thing as taking out this area. And so now we're left with this rectangle here. And this is now the short end, so we remove a square from that. So that's removing x. So x is square root of 2 minus 1. So I subtract that, and I still get a rectangle, so I can remove it again. And I'm left with a rectangle here. And this rectangle here is similar to this rectangle here. And how can I prove that? So this rectangle here, short side to long side is x over 1. This one here, short side to long side is 1 minus 2x over x. So we get x squared equals 1 minus 2x. X squared plus 2x minus 1 equals 0. So x is minus 2 plus or minus square root of 4 plus 4 over 2 is minus 2 plus or minus square root 8, which is 2 root 2 over 2. So x is minus 1 plus or minus square root of 2. We're only dealing with positive length, so it's square root 2 minus 1, as I promised you. So what this means then is with this rectangle, I can take off 2 squares, and I'm left with a rectangle similar to what I started with. I can take off 2 squares, and I'm left with another rectangle. So I can keep on taking 2 squares forever and ever and ever, and I can never stop the Euclidean algorithm. So this is another way of showing that the side of the diagonal to the square, diagonal to the side is incommensurable. Another interesting thing you can do with this is actually you can use it to make approximations to the square root of 2. So for example, let's say you have y over x as an approximation for square root 2 minus 1. How do you come up with a new approximation? Well, we let this be y and this be x. And so a better approximation turns out to be, so this is y over x, short over long. A better approximation is this over that. Okay, so we have a new approximation, which is going to be x divided by, well, what's this going to be? This is going to be y plus 2x. So if this is your approximation to this, this turns out to be a better one. So for example, if we approximate square root of 2 minus 1 by a half, by plugging this in, we get 2/5 as a better approximation for that.
Where did your x over y plus 2x come from again?
If you look over here, this is a square, this is x, and this is y. So this side of this is y plus 2x.
Okay.
So this is just kind of like vertical. And there is evidence that they actually use this kind of thing to actually come up with approximations. And so remember, finding approximations for square roots was important because square roots was actually something that was actually practical, well, from a math point of view. Okay, I think I'll stop there. Because I went so long last time, I wanted this one just to be short. So next week, we'll continue. I think soon we're getting on to the Hellenistic. We're at classical Greece for just a short time, and then we're going to the Hellenistic period after Alexander the Great. Any questions about any stuff? Okay. That will do us.